Okay, in the last section we did learn the derivatives of sine and cosine, and since we know those, we can use those derivatives of sine and cosine and the quotient rule to find the derivatives of the 4 remaining trig functions. And these you just have to memorize. The derivative of tangent is secant squared. The derivative of cotan is negative cosecant squared. The derivative of secant is secant times tan, and the derivative of cosecant is negative cosecant x cotan x. I do have a little trick to help you memorize those. I picked it up from the Calculus for Dummies book, which I highly recommend. But first we're going to do a quick proof of the first one. The other 3, I believe, are homework problems, and they're some of my favorite problems from this section. So let's move this up here a little bit. We're going to prove this one. Tangent, that derivative is secant squared. And they give us a little clue here. Tan of x is equal to sine of x over cos of x. I hope you remember that from pre-calc. Now we have the quotient rule. The derivative of the high function with the derivative of sine we already know is cosine. And we know that the derivative of cosine is negative sine x. So now we can take this derivative, d dx of tan x is equal to, and we apply the quotient rule, low d high. So we're going to multiply here on this diagonal. Cosine times cosine is cosine squared x. So low d high minus high d low. Sine times negative sine is negative sine squared x. Now we have a scenario where, and I guess I should finish that off, low d high minus high d low over low low. Cosine times cosine is cosine squared. A lot of people still at this level say, well, I want to cancel those cosines out. You can't do it because there's not a cosine squared in this term to cancel it out with. And again, back to that numerator. We are minusing a negative, so this is going to turn into a plus. Now, in that numerator, sine squared plus cosine squared, does that ring a bell from pre-calc? Sine squared plus cosine squared, that is a Pythagorean identity. That is equivalent to 1. 1 over, and we leave our denominator as cosine squared. And what is the identity of 1 over cos squared? Well, that's secant squared. Secant squared of x. And that's what we were looking to prove. The derivative of tangent is equal to secant squared. Again, the other 3 are left in the homework, and those are some good problems. Now, how do you remember these 4 derivatives? Again, this is from the Calc for Dummies book. The way they set it up is you're taking a test and you don't remember these derivatives, so you're trying to cheat. You're trying to get the attention of your buddy sitting next to you, and you say something like, psst. You try to make a noise to get their attention. Psst. Well, let's forget about that first letter P. SST. SST, those stand for 3 of the trig functions. Secant, secant, tangent. Secant, secant, tan from tst. Now, underneath them, I'm going to write their cos. Below this secant, I'm going to write cosecant. And this secant also, its co-function is cosecant. And tangent, if you put a co in front of it, you get cotan. Now, you just have to remember here to put a negative on that middle cosecant. So again, tst, spread it out, secant, secant, tan. Put the cos underneath and make sure that middle cosine or cosecant is negative. Now, to find the derivatives, we're going to go across the rows. If I want to find the derivative of secant x, it's these 2 multiplied together. The derivative of secant is secant times tan. Derivative of secant, secant tan. If I want to go in the other direction, the derivative of tangent is these 2 multiplied together. The derivative of tan is secant times secant, or secant squared. And it works also in the bottom row. The derivative of cosecant is negative cosecant cotangent. Negative cosecant cotangent. And in the other direction here, the derivative of cotangent are these 2 multiplied together. Negative cosecant times cosecant is cosecant squared. Example 8. Differentiating trig functions. And it looks like the first one, we just have a simple difference here of a couple functions. or got an x and a minus tangent, so we take the derivative, y prime. Well, the derivative of the first term, x, is 1, and the derivative of tangent is secant squared. Aha, part B. What rule are we going to need to apply? We got two things multiplied. Now it's x times secant. So the derivative of that first term is a 1, and the derivative of secant is secant x tan x. And we're going to have to apply the product rule. The first times the derivative of the second. The first term's x. The derivative of the second is secant x tan of x. So first derivative second plus the second times the derivative of the first is just secant of x times 1, or secant of x. And each term here, it does look like, has a secant of x. So we can factor that out. The secant of x times, well, we factored this out, so we're left with an x times the tan of x. X times the tan of x. Oops. And then plus, we factored this secant of x out, but remember, we do need a placeholder. There would be a 1 there. And I guess we would need that parenthesis over here. There we go. Ooh, and what's this note? Because of trig identities, the derivative of a trig function could take many forms. This presents a challenge when you're trying to match your answers with those given in the back of the text. I've seen this for the last for every year that I've been teaching calculus. A student will get an answer, and it will not look exactly like the one in the back of the book. It might be kind of close, but sometimes it might not even be close at all. And the answer that they have is correct because of those identities. And I think that next example goes into that. Yeah, example 9. Differentiate both forms of this. Here, if you take the first term, 1 over the denominator sine x, that's a cosecant. And then we'd have a minus cosine over the denominator sine is cotangent by another identity. So what we have here are identical functions. They don't look the same, but they are identical. So what I'm going to do here is draw a dividing line right down the middle. And over here, we're going to derive this function with the quotient rule. And then over here, we're going to derive this function just by, it's a sum or difference. So we'll just take a nice quick derivative over there. But the first one, the upper function is 1 minus cos x. That derivative, the derivative of negative cos, is positive sine x. And in the denominator, the derivative of sine is cosine. We do our derivative, y prime, low d high is sine x times sine x, or sine squared x, minus low d high minus high d low. So here we're going to multiply across this diagonal, and that's cos of x times the quantity, 1 minus the cos of x, all over low low. Sine x times sine x is sine squared x. So distribute that cos of x across those parentheses. We're going to have a minus cos of x, and then negative cos times negative cos is plus cos squared of x. Ooh, something's going on there, over sine squared x. So what can we simplify further in the numerator? Sine squared plus cosine squared is equal to 1. 1 minus that remaining cos of x over sine squared x. And there we go. That is our y prime when we derived this form of the equation. But if you had taken this function and used your trig identities and manipulated it into this and then found the derivative here, y prime, let's see, the derivative of cosecant is negative cosecant cotangent, and then minus cotan, the derivative of cotan is negative cosecant squared, so that minus, and there will be a negative cosecant squared, so that'll turn into a plus cosecant squared x. There is basically just one step, and now we have two derivatives. And these are both, identical. Again, we use a derivative to find a slope at a point or an instantaneous rate of change. If I graphed both of these functions, the graphs would be right on top of each other. They would coincide. If I wanted to find the slope at a particular point, I could take that point's x value and either plug it in here and get the derivative, or plug that same x value in here and you'd get the exact same value. Okay, I think this is about the last topic here for this section. Yeah, we'll go over this in example 10 and we'll be done here. And this is easy. It's just higher order derivatives. Just as you obtain the velocity function by differentiating the position function, you can obtain an acceleration function by differentiating a velocity function. Another way of looking at this is you can obtain the acceleration function by differentiating the position function twice. And we talked position and velocity in earlier sections. Here's our position function, s of t. We usually use t to measure in time. If we take the derivative s prime of t, that gives us the velocity with respect to time. Now, if we take this velocity function, s prime of t, and derive it again, s double prime of t, that becomes the derivative of the velocity function, or what we'll use for acceleration. And what I mean by, a second derivative, if we start out with x to the fifth, that would be, let's just call that y equals. Well, what's y prime? Y prime would be 5x to the fourth. Can we derive that again? Y double prime. Just, use the power rule again. 5 times 4 is 20, x to 1 power lower, down to the third power. We can do the third derivative, y triple prime. Well, just derive again with the power rule. 3 times 20 is 60, x squared. And the fourth derivative, I think we'll just, instead of primes, we'll use just a little like an x or a upper script 4, put it in parentheses so you don't think it's an exponent, and that would be 120x. Those are just the higher order derivatives. And if you want to think about this in terms of physics, remember we have our position, where it is located. We have the velocity, how fast it's moving. Velocity is, we take the derivative for a rate of change. How fast is the position changing? That's the velocity. But how fast is the velocity changing? Is the velocity picking up speed? Is the velocity increasing? Is the velocity decreasing? That is our acceleration. Positive acceleration means it's picking up speed. Negative acceleration means it's slowing down. And again, for the notation, for our different calc notations here, first derivative, we got y prime or f prime of x, or dy dx, or d dx of f of x. Our second derivative, we just add an extra prime, y double prime, or f double prime of x. Or if you want to do the dy dx notation, you sort of give it like these little upper scripts here. In the numerator, the d gets it. In the denominator, the variable that you're deriving with respect to gets that. So d squared y over dx squared, and then y triple prime or f triple prime of x, and so on and so forth. Last example here, example 10. Find the acceleration due to gravity. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of the falling objects is given by s of t equals negative 0.81 t squared, remember t is for time, plus 2. Where s of t is the height in meters, so we're going metric, and t is the time in seconds. What is the ratio of the Earth's gravitational force to the moon's gravitational force? So I guess we're going to look at this in two pieces. I'll just do a divider line right down the middle. And we'll do the moon, since that's what we're talking about here first. And we'll also do the Earth. And then we'll make a ratio of those two gravitational forces. And we're going to do our three derivatives. We're going to have our position function, our velocity function, and our acceleration. And we want to get down to acceleration and then compare those in a ratio. So the position function for the moon, let me switch over here to red, s of t, this is just given right up at the top of the slide there, negative 0.81 t squared plus 2. Well, the velocity function is just the derivative of the position. S prime of t is equal to, take the derivative here, that would be a negative 1.6 2t, and the 2 would derive off. And then the acceleration function, we take the derivative of our velocity function. S double prime of t would equal 2. Here the t is to the first power, so that would just derive right off, 1.62. That is the moon's gravitational force. Now they want us to compare that to Earth, and if we flip back, I can't remember if it was in the last section, we looked up the Earth's gravitational force, and that was negative 4.9 t squared plus v sub o times t. V sub o is just a number, that is initial velocity, plus s sub 0. And that s sub 0 was the initial height. So we're just going to do the same song and dance here. Take the derivative. S prime of t is equal to, here, just apply the power rule right here, and you're going to get a negative 9.8 t plus, now here we had just a 2 and that derived away. When we took the derivative here, 1.62 t to the first, we just derived the variable off. Even though we don't know what this coefficient is, that v sub 0, no matter what, when we take the derivative, this t is just going to derive away, and we're going to have v sub 0. And that's just some number. It would change with the different problems. Now, if we take the derivative of that velocity function, s double prime of t, and apply that power rule again, here the first term, derivative of negative 9.8t, is negative 9.8. And no matter what this number was, it's now just a constant, so that's just going to derive away, and it's gone. So here are the two gravitational forces, and we were asked to put those in a ratio. The ratio of, and they listed it as Earth first, Earth to Moon. So when we set up our ratio, we would write it as negative 9.8 to negative 1.62, which is approximately 6 times, roughly 6 times. And what were they specifically asking about again here? The Earth's gravity. So the Moon to Earth's gravity, the Earth has about 6 times the gravity that the Moon does. And that's the end of the section. That is the 3-3 product rule and quotient rule. And then we touched on these higher order derivatives. And now I see down in the corner we do have a box. What's in the box? Because I don't see that in my notes. Aha. They give you the mass of the Moon, the mass of the Earth, the Moon's radius, the Earth's radius. Because of the gravitational force on the surface of a planet is directly proportional to its mass and inversely proportional to the square of its radius, the ratio of the gravitational force on the Earth to the gravitation of the Moon is, and here they just did it all with, the big numbers using some scientific notation there because these numbers are huge. You make that ratio and you get approximately, 6 times the gravity on Earth. I'll see you for 3-4.